Now I want to talk a little bit about magma characteristics, magma properties, such as their chemistry, their viscosity, and their ability to hold volatiles or water. So rhyolite magma, for example, is considered to be a felsic or silicic magma because it is high in silica. For that reason, it's also very viscous, and it's able to absorb or dissolve lots of water. So, so often rhyolite magmas are thought to have the potential to be very explosive because they are high viscosity and they have the ability to dissolve a lot of water. Basalts, on the other hand, are considered to be mafic magmas because they contain not very much silica but are dominated more by iron and magnesium. And for that reason, they're darker in color than rhyolites. They tend to be low viscosity and low water content, which is why typically we associate them with effusive or gentle eruptions. So those are a couple of the characteristics of magmas that are important in terms of dictating the style of eruption that they can produce. And then in the next moment, we'll talk a little bit about viscosity. Here are some useful comparisons. So I want to draw your attention to the basaltic lava in the red arrow. And the viscosity of basalt is approximately 160 Pascal seconds. Well, what does that mean? It's somewhere between mayonnaise and creamy peanut butter. Rhyolite lava, on the other hand, which is the gray arrow, is 10 million Pascal seconds. That means it's 100,000 or nearly 100,000 times more viscous than basaltic lava. For that reason, you're more likely to have the rhyolite lava go through that fragmentation process, and the basaltic lava is much more likely to flow like a fluid. So that's where you get some of the decisions being made about how these magmas are going to behave in terms of explosive versus effusive behavior. The other component are the gases. So the water vapor is the most common gas, and that drives most of the explosive activity. And if it's trapped inside a rhyolite lava that is very viscous and really wants to hold those bubbles inside, then you're more likely to get an explosive eruption. Those gases, which are less common or less abundant in a basalt, also escape the basalt more easily because it's lower in viscosity. So I hope that clarifies a few things. Now I want to talk about the dangerous things that volcanoes produce, the dangerous phenomena that are produced by volcanoes. Remember, I called this earlier phenomenology. This is an opportunity for us to watch these kinds of things in action to get a sense of their scale and to get a sense of what hazards they pose. We've already looked at lava flows, and lava flows tend to be associated with they build gently sloping volcanoes. We saw a few videos of these guys in action in Russia. Now I want to take a look at another environment in which lava flows form, and that is in a fire fountaining fissure. So you have these Icelandic eruptions that tend to come from elongate fissures. They produce fire fountains and lava flows. So let's take a look. So here we're looking at the eruption of Halaron from above, from a helicopter, and you can see the fire fountains, and you can see that they're in a long chain. It's not a continuous chain, it's sort of episodic, and you can see there's a lot of gas being produced from the same vents. And this fire fountain here is on the order of a couple of 100 meters high. So let's take a little bit more of a look. Here's something I want to show you. So this is the chain of fire fountain vents along this rift, along this fissure. And then this lava flow is forming. Where does that come from? That is being fed by this fire fountain. So as the fire fountain continues to erupt, the lava is then sort of deposited on the ground, and that deposited fire fountaining product produces this lava flow. So this stuff is very hot, and it stays hot and stays fluid in order to feed this lava flow. And you can see as well that that lava flow is flowing approximately downhill, and it's forming a little bit of that crust that we saw in the previous videos where you have those darker portions, so it's cooling at the surface and forming a little bit of a crust, and that crust will continue to grow as it goes downstream. The other thing I want you to notice, and as I continue to play this video, is what's happening at the edges of the fire fountains. You'll see a little bit of ash being produced, and you'll see clots of lava being thrown from the fire fountain. So let's take a look. So here you can start to see those clots and ash, and even in the nighttime shot you can see those clots are still glowing. So that's a good example of the fire fountaining from a fissure. Also a good example of fire fountain fed lava flows. Now let's move on to activities that are generally associated with more viscous lavas, rhyolite or similar lavas. Let's start with this picture here on the upper right where we have a volcanic plume. And the volcanic plume will produce ash and tephra fall. So that's the stuff that's falling out from this umbrella region. And that is hazardous for a wide range of reasons, and you'll learn more about that in one of your exercises. So let's take a look. So this is the eruption of Calbuco volcano in Chile in 2015, and this is a great image of what an eruption plume looks like and how it evolves. Okay, I'm going to pause it right there. Remember, we also saw this with Mount St. Helens. You have this rising jet and plume, and it rises because it's less dense than the atmosphere. And then when it reaches a height of neutral buoyancy, it spreads out. And in this particular case, you can really see all of these particles that are falling from that umbrella portion of the plume. So let's just watch it a little while longer. There it is, also from space. And this is another view, and again you can see that ash fall coming from that umbrella portion of that plume. Now let's move on to pyroclastic flows. So pyroclastic flows are in many ways the opposite of the plumes. They are not buoyant in the atmosphere, but rather they're denser than the atmosphere. For that reason, we often call them density currents. Density currents hug the ground, which means that they're that much more dangerous to humans on the ground and human property on the ground. So this is the cartoon image of what these things look like. They're clouds, but they hug the ground, and they're hot and very dangerous. These pyroclastic flows can form in a couple of different ways. This first one I'm going to show you is a small example. So it's an example of very small pyroclastic flows from Montserrat in the Caribbean. And what happens here is that the jet plume is not sufficiently buoyant to rise in the atmosphere, and so instead it collapses and produces these ground-hugging flows. So let's just take a quick look here. Now you can see the jet. Part of it is rising as though it's buoyant, but then you start to see things hugging the ground. So look to the left and to the right of the plume. You can see a little bit to the left. Oh, but what's happening to the right? You can see something that's traveling along the ground towards the sea down slope. And the noses of those things are probably 100 meters high. And you can see it spreading out. And they're probably 400 degrees centigrade. So this is not the kind of thing that you would want to be caught in. This would completely bury any homes in its path, and typically things would catch on fire. Here's another example of the way in which pyroclastic flows can form. This is Unzen 1991, and it is an avalanche from a hot lava dome. So let's take a look. So this is the Unzen lava dome. It's made of very viscous lava. It is still very hot, probably 800 or 900 degrees centigrade. So this avalanche is also very hot. And what you can notice here is that it's traveling in the riverbed, and that's a characteristic of pyroclastic flows. In this particular instance, it's kind of overtopping some of the hills. So if they're voluminous and fast, they will jump over hills. But typically, they will be confined to river valleys. So let's watch that one more time very quickly. So the avalanche initiates because lava domes are very unstable. And this is a common occurrence, a very hazardous occurrence. And so what you can see early on here is that the tendency for this thing is to stay in that river valley and follow the low-lying areas of the topography. But if they're big enough, fast enough, they can overtop hills. These are the most dangerous things that volcanoes produce. Now I want to draw your attention to volcanic mud flows, otherwise known as lahars, which is an Indonesian word, and this is typically what volcanologists call them. This is an example from Merapi volcano in Indonesia, and I'm going to show this to you just to get a sense of how these things look when they're in action. These are a secondary process in that when you have an explosion or pyroclastic flows, you produce a lot of ash and debris, as you saw in the previous videos. If there's a heavy rain or some kind of dam break, that water will mobilize all of that ash and debris in a very, very destructive mud flow. So here you can see it's almost like hyper-concentrated stream flow, so it's mostly water with some mud. And as we go through this video, you'll see that there are parts of this thing that are more mud-rich. But see how quickly it's moving? It's like flowing concrete. And there's something I want to point out here. So now you can see in some parts of this that big boulders or blocks are being moved. Right there's one. Do you see that large boulder? So these things have significant carrying capacity. They aren't just a stream. They're much more momentum than ordinary stream flow. And these blocks and boulders and this concrete-like mixture are very damaging. The eruption of Nevado del Ruiz in Colombia in 1985 produced a lahar overnight that destroyed the town of Armero and caused tens of thousands of fatalities. This example is discussed in your book, and I suggest that you read this carefully as an interesting case study of what can happen if people down slopes from volcanoes are not prepared for things like lahars or pyroclastic flows. Here I want to revisit the hazard map that we looked at before. This is from Colima in Mexico, and it shows nicely the areas that can be affected by the different phenomena we just looked at. So the orange and red are the expected pathways of pyroclastic flows, lava, and then the green or teal color is the expected pathways of lahar inundation. So if you notice, all three of these, pyroclastic flows, lava flows, and lahars, have this long snaky-like character. This is showing us that these phenomena tend to stay confined or almost completely confined to river valleys and channels. You can notice here where perhaps the channel from the volcano opens up and that these pyroclastic flows are expected to spread out onto more flat ground. But the shape of these patterns on this hazard map show you or demonstrate clearly that the expectation is that lava flows, pyroclastic flows, and lahars will be concentrated around low-lying areas and river channels. Bombs and ballistics, on the other hand, can go in any direction because they fly through the air, and they can get to a kilometer or two from the vent. But the biggest footprint of any kind of hazardous phenomena is the ash fall. So that's what's coming from the umbrella cloud. That's what's falling from the umbrella cloud. You have this rising plume, and then it spreads out at height of neutral buoyancy, and the ash and pumice fall from that umbrella. That umbrella can be carried to great distances by the wind, and it alone, without the wind, spreads out in all directions. So that's what you're seeing in the gray portion here, is the potential footprint from the umbrella cloud. And even though ash fall is much less deadly than pyroclastic flows, its footprint is much greater than pyroclastic flows. And you can see that quite clearly in this map by the areas that would be expected to be affected by pyroclastic flows in red versus ashfall in gray.